Hello, everyone, and welcome to the Geek Narrator podcast. I am your host, Kaivalya Apte, and I am back with another episode on streaming, on data streaming, on real time analytics. Today, we are going to talk about Timeplus, and we have Jove from Timeplus, and he's going to talk to us about streaming and analytics and how Timeplus works, how the core engine, which is Proton, I believe, works internally. So, welcome, Jove. Thanks a lot for joining us today. And I'm really excited to dive deep into the world of streaming with you.
Yeah, hi Kevin. Yeah, I'm so glad to join your podcast. I've been watching your episode for a long time, and it's really great to be talking and sharing about what we are doing right now here at Timeplus. I'm one of the co-founder, and we are very excited to make things about data streaming much easier, more affordable, and more productive for everyone.
Yeah. Let me try to define the problem statement first, right? A lot of companies have a ton of data sitting in different systems. It can be like historical data, it can be like real-time streaming or the event stream that are coming in. And each data source is different. And what they want is combine the power of historical context of data and also the real-time aspect of data that is coming in right now at a high pace, at a high volume, and make sense out of it such that they can drive business decisions out of the context, out of the value of the information. So that is the problem statement, right? And they want to do it as fast as possible because time is really critical here, because as soon as it gets delayed, that insight that you're getting from the data might not be as valuable, right?
Yeah, that's right. That is, people naturally want the fresh results, right? They might, it's right. That's the thing, that is, you cannot make decisions within 20 seconds as a human being. But right, so if your server is being attacked, if you are, so there's some sort of crash, or there's other important stuff like IoT sensors, whatever. So you do want to have a way to prevent bad things happen, or like do some other things, even without human involvement. So people really want the fresh results, have some fresh alerts, and it's also, the data can be consumed in different ways. So people want the real time things, but also the streaming really push to the next level, which is you continuously calculate, you can continuously analyze and alerting. Yeah, but we can talk more. But overall, I think when in this modern world, people are used to those Ubers or DoorDash. They really enjoy, they can see what is happening right now. And on the enterprise side, on the developer side, people really read the bar and want to see what is happening at this moment. Yeah.
Yeah, that's right. That's right. And as you mentioned, even a little bit of latency in receiving data or in processing data or anything that might end up delaying the entire latency of the pipeline might impact the business actually, because people are actually, or businesses are actually making critical decisions based on real-time analytics. What are some of the use cases, or let's say the business cases that you have seen where people really use? So you mentioned DoorDash and Uber, right? What are some other examples in your experience that people really rely on these real-time insights?
Yeah. One of the typical use cases, which is also one of our key focus in Timeplus, that is on the fintech area, right? So they get very fresh data regarding what's happening on the market.
Yeah.
They also try to understanding, say, what's that being discussed on Twitter, what's being discussed on Hacker News. Everything combined, they might want to understand better about whether it's a good time or moment to buy or sell or hold. And even if we don't talking about those social listening parts, just look at the data itself. And if you can get very fresh data, say multiple data points within 1 second, then if there's a lot of buy and even at a different volume, you might come up with some algorithm-based trading to give the signal whether you want to buy or sell. Right? And that really don't have to be human involved. You really build a very good algorithm and based on what is happening right now, but also you have to making sure in the past that kind of data and pattern can give you good return. So this is what we call backtest. So in the fintech area, streaming or real time is really a very important thing to make them reach or to prevent the potential loss. But also in other cases like IoT sensors or in weather, in almost every part of data, you can understanding about what's happening right now, then you have a better chance to make better decisions.
Yeah, that makes sense. Let's start with giving an overview about Timeplus and why do companies need a product like Timeplus? Like, what is the benefit?
Yeah, of course. So I'm wearing the t-shirt from my company, Timeplus, right? As you can see, very clearly that it is about the time. And it's time plus, say, database or time plus solution. So we really want to add time as the first citizen in our product, in the service. But this is a company we have been working for 2 years at seed round, and many of us in Time Plus, including me as co-founder and CTO, we all coming from a company called Flink, right, which is a very successful big data company and also doing very good business on the log analysis, on the IT monitoring, on security. So the reason why we really see a strong need to build a company like us is there's a lot of good solution out there. There's a lot of good database. There's a lot of log analysis, but the people keep raising their expectation to get real-time insights. Right? For example, in my previous employer, which is Flink, if you have thousands or tens of thousands of servers, you really want understanding about what's my server usage, whether they are crashed, whether they are being attacked. So those informations can really drive very critical business decisions. Not really about like auto-scaling those IT stuff, but also for the security part. You don't want to wait for a half hour to understanding certain port is opened accidentally and your database is being scanned by some other folks, right? So in that case, the strong requirement from customer that is, hey, can I see what's happening for the past, say, 2 minutes? Because again, for example, Splunk had been there for almost 20 years. At the very beginning, people were very happy to see what's happening for past 1 hour, and they turn to half hour at 10 minutes. But there are certain limits for architecture like Splunk to get to real-time things, right? Maybe some of the big customers with a lot of servers with a very careful, well-architected design, they can down to maybe 2 minutes or 1 minute, but they can go for lower, right? So it's very hard to get what's happening for the past 2 seconds because how things work, that is, it will have to keep rescanning everything. So by rescanning everything, you end up with A, you waste your disk IO, B, you waste your CPU, and also you have to see what's the delta. So there's a lot of different things. And so we, at Splunk, we start using technology like Flink or Kafka, try to build a data streaming component before we send data to the index. So that's product we call data streaming processor, DSP. So it is a very big project with a lot of components. And actually, many of us, we really see this is the right direction. But again, that is, we feel like there can be some different ways to doing. For example, we at the Timeplus, we think it would be great if we can leverage the low-level operation system or the latest features from the hardware to further reduce the latency, which is not really commonly available for the JVM ecosystems. So that's why we went to the direction to leverage Clickhouse, for example, which we will talk about later, and also many other awesome C++ library and best strategies to come up with a super low latency and performance system to solving the data streaming system, the problem. And some other members in our project, they really want to push Flink to the next level. So they have some other companies around data streaming. But again, we are very passionate that is data streaming is the future. And we just try to solve this in different ways. But based on different use cases, people may choose which one is better work for them. But again, back to us, that is, we have been there for 2 years. And we offer a cloud service. So if people don't want to manage their data streaming infrastructure, they can leverage our fully managed service in the cloud. But in the same time, we also offer not just on-prem deployments. Actually, we also open sourced our core engine 3 months ago as a project and using the Apache D2 license. So that can be really great for anyone who wants to start data streaming or want to move to the next level of data streaming. They can leverage our open source project, no matter as a Docker image or as a single binary, to get health data and see what kind of amazing real-time insight they can build with the Timeplus Proton.
Yeah, that's interesting. And you mentioned about Apache Flink. You also mentioned Kafka. So let's compare with Apache Flink and Kafka streams. They have also KSQL, Flink SQL, and then what Timeplus brings as a product, right? And you also mentioned about the problems of garbage collection on JVM, and it might not be suitable for really high performance, ultra low latency applications but even the garbage collection has improved as compared to the previous world.
Yeah.
So how do you compare it with the existing frameworks or products like Flink and Kafka streams?
Yeah, me as the co-founder in Timeplus, my primary role is head of product, right? But also I do some random stuff like UI design, like a little bit marketing. But it's really key for me to understanding about the landscape of the current data streaming and what's the offering out there, not the commercial open source, and what's but also the pain points and the opportunity for us to shine and further help the developer to be more productive or cost effective. Yeah, that's right. That is Kafka and Flink. They almost came out in the same time, like 9-10 years ago. And Flink is very focused right now on the streaming side. And Kafka is very popular and almost a de facto standard for data streaming. At least for the data storage processing side, also the API become really well known, and even there are some Kafka alternative, but they are still support the Kafka API. So you don't have to change your code. You can talk to their system, but still using Kafka. So it's very popular for Kafka. And the amazing thing for Kafka that also is you can choose the way how you process data in Kafka. You can process it in the real-time way, in the streaming way, but also you can choose to do this in a batch way because, say, for example, for some reason, you don't want to keep running your server to process data in Kafka. You can shut this down and maybe 5 hours later, you can start your program and then we can read from the previous offset. So it's more like batch, right? You can do this like hourly basis or daily basis. But so the Kafka stream is, I think that's a good attempt in within the Kafka ecosystem to not just focus on the storage side, but also how to consume the data with more building blocks. Otherwise, you have to leverage the very low level Kafka consuming and producer APIs. But using Kafka stream, there's some concept regarding how to somehow create a stream, how to read it efficiently, how to query it. But also there's the other layer is the KSQLDB, which is built on top of Kafka stream, providing the SQL interface. But one of the, I would say, I'm nothing fundamental, but one of the common challenge for people using Kafka stream or the KSQL is that is the assumption that is all the data is in Kafka, which is, I would say, not necessarily wrong, but bring some challenges. For example, some customers, they might be using AWS Kinesis, for example, right? Or they might try other alternatives like Apache Pulsar, or they don't really have a consolidated data streaming platform. They might just have sensors on the IoT. They might have some data on the internet. On one side, no matter KSQLDB or KStream, the assumption that all the data is already arrived in Kafka, which can be okay, but not always the case. And some other challenge that is the data have been in Kafka when you process it, right? It is okay you put, say, last 1 week or 2 weeks data in Kafka, but it's unlikely you put like 2 years, or which we talk about like some compliance, you might have to put data somewhere for 7 years. It's not a typical use for Kafka to be the long-term storage. I know there's a lot of attempts, or even I attend some of the new announcement or meetings from conference that the tier storage is upcoming, and the tier storage is also available in other systems. But again, it is not a best practice, I would say, at least for now, to put a lot of historical data in Kafka. And the part 3, that is, even you have all the data in Kafka, there's no really, for example, index, right? You have a lot of awesome talk in your program regarding databases. So one of the fundamental things about database that is not just store, but also you have to build the index to make things faster, right? You want to understanding, hey, what's the max value, what's the count? You don't have to want to scan everything, but that's basically how it's working for case Kafka stream or KCQ. That is, if you run a query, you have to rescanning all the data. So it's probably not the best way to process data in that kind of scale. So that's some of the challenge. And there's other kind of consequences or side effects using Kafka stream or KQDB. That is, it is really a raw Kafka ecosystem. They don't really want to bring too many other components. So for example, certain part of the state, they actually put back to the Kafka as a special topic or internal topic.
Yeah.
I know there's some data is put into the, for example, RocksDB, which is very common for today's modern open source projects. RocksDB is not in Java, but they have a good branding. So some state in RocksDB, but still there's many other informations is put into the internal topic in Kafka. So you end up with, hey, I needed to scan, for example, 2 GB per day as the data in my original Kafka topic, but you might end up with certain percentage of data, I don't know, maybe 1 GB or more or less as the internal state in your Kafka. So you will see more number of Kafka topic, and also they consume more storage on the computing resources. Yeah. So again, people really passionate about data streaming, and I know there's a lot of passionate users using Kafka Stream, and the KCQDB is a really good technology, but we still think there's different ways to doing so. So that's why, for example, Timeplus, we have a solution, and Flink is very in a kind of different way. That is, it's a neutral. It's not so bounded to Kafka. It can very good support for example, pulsars or the technology, and they have amazing system like watermark, all those things to really give you very flexible way to process the data. You can choose either the data stream API, or you can leverage the SQL interface. But historically, that is, Flink has been there for such a long time. We're talking about 10-year anniversary next year for Flink. And Flink 2.0, they also moved towards the new direction to have unified processing, not just about the streaming, but also the batch, even be the storage, kind of like data warehouse, or they call this streaming house. So not just on the processing side, but also the storage side. So to maximize the value for customers. Again, there's a many different way to process data in Kafka or in the real-time side, but we hopefully for Timeplus, we can provide alternative if you're really looking for is low latency, like lower latency than say Flink or KCQ stream, or we can come up with like single digit millisecond because there's no Java, it's all in super fast. We leverage the latest feature from the OS or from the kernel stuff. We can get the lower latency, but also we have higher performance. And the other thing that is we try to make this entire process of data streaming processing as easy as possible.
That makes sense. And there are some really good points that you mentioned. So one is about Kafka Stream. So it's an amazing framework, like people use it. But again, it has this requirement that you need to have a Kafka cluster, and you may not always have your data inside Kafka. And it's not a big challenge to get your data inside Kafka. There's CDC supported connectors. You can get your data into Kafka. But again, it adds up to the end-to-end latency is what I imagine, right? Like you first get your data into Kafka, and then you use Kafka streams to process, to do real-time analytics, and then maybe dump it into some other data store or something. So all of it adds.
And that's also adds some other operational cost, right? You have to set up, maybe
that's right.
Not a single node Kafka have to be a cluster.
Yeah.
That it's not cheap or easy to operate a production Kafka. Yeah.
That makes sense. If you are working at a company where, Kafka is heavily used, there's a team who has experience managing Kafka cluster and everything around operational excellence on working with Kafka, then go for it. It's totally fine. But let's say for smaller companies who don't have much experience with Kafka, and just to use Kafka streams, there is an inherent dependency on Kafka. It's not always the best deal. You also mentioned about Flink. Again, Flink needs a good experience. Managing a Flink cluster is not easy. There are companies out there who can do it for you. But again, it's on the JVM. And if I'm not wrong, Flink is again only about the real-time streaming use cases, right? Does it also provide you the historical? You mentioned they are working on something stream house or like a data warehouse solution where they also have data stored for longer duration, and they're trying to mix the streaming use case with historical data analysis. But that is still not there, right? Is what I understand.
Yeah. For Flink, they emphasize on the unification of streaming and a batch for a while, right? So
Yeah.
not really this year or last year, it's been for 5 years, I think.
Mhm.
So, but the way how it works before the Apache Pymon came out in the Flink side for the batch or historical analysis, that is, Flink built a very good ecosystem regarding the connectors.
Yeah.
Right? So you can have a connector for Kafka for sure, but also you can have a connector for, say, Postgres or other systems. So when you want to understanding what's happened for the past 3 months, you can still leverage the either Flink CQ or the data frame API, but you leverage this connector to go back to the time you want to start to analyze, and the data go over through Flink again. So it's more like, in that case, there's certain similarity for Flink and Spark, right? They can process a huge amount of data. The difference that is Flink allow you to do this in a much like true streaming way, not something like macro batch in Spark. But again, they can process a lot of data, but the assumption is you can leverage your connector to go back to the previous point, because Flink itself don't really own the data itself. But things now become interesting because they see the rise of, say, Iceberg or the S3, all those things. And they think, if I can have an efficient way to process data in my own system, in my own format, then I don't really have to talk to other systems. If the data is not available in their system, or it will be too expensive to talk to other systems, if I can process all the data in my own data warehouse or the streaming house, things will be much easier and or more controllable, or there's more room to optimization. But in our case, we build a Timeplus in the way that it is a database with streaming ability. So you can put any kind of data in Timeplus or Proton for like arbitrary length, for example, 1 month or 2 years. It's up to you. It's as good as Clickhouse, right? So you can imagine it's very solid and mature OLAP systems for sure. Even you can do some certain kind of range search for the raw data. You don't have to be always aggregation. But with our actual components and the design, we can give you very powerful and intuitive way to do stream processing. But something very similar to, say, Flink CQ or KCQ. That's hopefully can bring the two worlds together. That is, you don't have to choose which one is your streaming processor, which is your OLAP. Actually, you can just have one single component or single process or single binary. You can get both. You can query in the streaming mode, you can query in the batch mode, or you can even have a CQ to query both ends and do some lookup or do some detection.
That makes sense. And you also mentioned about the latency part. As you mentioned, Timeplus. So time is very important concept. And your website also talks about 4 millisecond end-to-end latency. So I'm really curious about how do you achieve. So apart from being implemented in C++ and being able to use the latest feature of the hardware, I want to go deep into the optimizations and how things are actually working to get that kind of low latency. So let's start with a little bit of understanding of what kind of components I'm looking at, how the ingestion is working, because that's let's say the first step of getting your data inside Timeplus. And also let's use this to dive deep into the core engine, which is Proton, and how all that works. Yeah, let's start. Let's maybe take an example. Let's say stock price. So let's say an event stream coming in, and there's also historical context or how stock prices were changed and all that. And I want to use Timeplus, or let's say Proton as my engine to query real-time analytics and real-time insights, and also some historical use cases. So how would the ingestion part work?
Yeah. So let's from that. Again, the fintech area is really our strong focus as a company. Also for even our open source Proton community, we get a lot of inquiry or discussion regarding people coming from fintech or Web3 cases. So it is, again, the data quality is good, and there's a strong motivation or intensive way to motivate you to get real-time insights. If you can be like 20% faster than your competitor, you might have a better chance to get more money or reduce the risk. But That's true. That is, people in the fintech area, they have data in different formats. I do notice some customers already using Apache Kafka as their internal standard for anything data streaming. So all the data is available in Kafka. Some customers also trying to use Apache Pulsar if they have, say, more, for example, they have multiple teams, they have different geolocation. Pulsar may give you a better multi-tenancy and cross-site synchronization kind of feature like that. Even there are some other customers, they focus so much on this latency and the performance, they even have their proprietary protocol formats. So let's talk about it one by one. So for the Kafka side, things are much easier because we do provide out-of-box support for Kafka in Timeplus or in Proton. So the difference that is in Timeplus, so let me put it this way. In our Timeplus cloud, we also using the Proton, the same component as our engine. So that the same engine in our cloud, the same engine in our commercial offering, and also in the open source side. But in the cloud side, because we want to further make this intuitive and easy to use, so we have a nice UI, and we support a wide range of sorts and things, which is not always available. So the strategy or our line is, so for the Kafka, those the first tier data source or destination, we will implement them in Proton in Timeplus to get the lowest possible low latency and high performance. However, if you have many other data sources, for example, there's a lot of ask in the Web3 community talking about WebSocket, for example. And it is possible to implement WebSocket in our Timeplus code base, but it will take longer. And we don't want to create too many sort of things in the C++ part. And that's why we leverage a component called Benzos, which is written in Golang and have a very rich component regarding sort of things. But how this Benzos as a microservice in our cloud talk to Proton is through our REST API. So Proton as a database, and similar to Clickhouse, we support, for example, you can run insert into as a basic way to add data. But if we're talking about tens of thousands events per second, you don't want to generate a bunch of into, it's not efficient at all. So we do focus a lot on our streaming ingestion API. So the REST API allow you to push any data to us in the most efficient way. So you can push events one by one, row by row, but also if you push 1,000 events, you only needed to share the column names once and a bunch of other rows in the body. So it's a very compact format to efficiently transfer data to us. And also, unlike Clickhouse, which is also based on our primary engine for our historical side, but Clickhouse inherently, it doesn't really support good small batch scenarios, right? They call parts as a file and later on merge those parts together for the merge tree. If you keep pushing data like small batch, like every 10 events per request, you end up with too many small files. It will create extra burden to merge data. But in our case, we have this streaming REST API, but we have streaming storage inside the Proton process. So it's not a separate process. So again, we have a strong opinion regarding how simple things should be. There's nothing more simple than a single binary, a single process. So Proton is a binary. You can just download and run it, or you can install for sure. But if you don't want to install, you just run it in the current directory. So everything is inside this process, but there's a certain part of the code is acting as a streaming storage, or put it in the other way, it's acting as a Kafka, but it's not that general purpose, right? It is very common that is, for example, if you don't use Proton, you have to set up a Kafka to accumulate your data, then you have a Flink to process the data, then you send data to OLAP system like Clickhouse. But in our case, this Kafka, this Flink, this Clickhouse actually is in one single code base and in one single process. So back to your question, that is how we can consume data in Kafka. That is, we have the native support of Kafka protocol in our Proton. It is part of our we call external stream. So you can define a stream, just define a table in Proton. But in this case, you don't have to insert data piece by piece to the stream. It's actually query the external system. For example, we do support Kafka today. We are going to support the Pulsar soon. We also have a special integration for file. So we can talk about this later. That is, we can actually leverage Proton for log analysis for the real-time stuff. But again, to the Kafka side, we leverage the Kafka. I think this lib Kafka is a C++ library of Kafka to talk to Kafka efficiently. Then we can move data in and put into us. It will be arrived in our streaming storage first. Then it will ship to our historical storage so that you can leverage more power of ClearHouse, for example, like index or codec, to efficiently query data later on in the aggregation way. But all the process is streamlined in a single binary or engine.
Yeah. So let's take a pause there just to understand what is exactly happening. So you mentioned for Kafka, of course, you have very good support to get data inside your system. And the most important thing you mentioned was everything is in one binary and it runs as one process. So when you say everything, it's basically the storage part, which is like Kafka, and then the analytics part, which is, let's say, Flink, and then the historical analytics, which is Clickhouse. So is Clickhouse somehow embedded inside Proton, or how that is working? And the second question I have is, where is it all fitting into my application? Is it running as a separate cluster where there are multiple processes running and each process has different parts to it, which is data storage, which is stream processing, and also analytics? And there are multiple processes like this running on a cluster?
Yeah, sure. If you check our GitHub repository of Proton, we mentioned this is powered by ClearHouse. But again, people, if they don't read the entire thing, they might have a different understanding. Some people say, oh, you might have ClearHouse as part of your deployment. Which version should I use, for example? But you don't have to worry about that, because we actually take some of the code from ClearHouse and make some changes to better fit our design, which I will talk later. But as a user, you get a single binary. I don't know, maybe right now it's before 400 megabytes binary, and it's compiled to like Linux or Mac. We don't support Windows as binary, but you can run Docker on Windows for sure. It is part of our code base, and we keep a good collaboration with ClearHouse as a company or as a community for each other. For example, we also submit quite a few pull requests to the ClearHouse community to contribute back. For example, we somehow so focusing on the data streaming side, and that's also part of the item in their ClearHouse community or company roadmap, but they don't really have so much resource or time focusing on that. I think they are really start a lot of effort on the cloud with data warehouse, the cloud native design, leverage more about S3, stuff like that. So they are very happy, company like us, to push ClearHouse further, adding a lot of data streaming capability. So we have some good communication with the community and the company. But in our case, we leverage ClearHouse as the basic OLAP system regarding the storage, regarding the SQL functions. However, we made some changes. So for example, one key change is we have our own data format. So as a user, you put some data in your Kafka, and the Kafka data is poured into Proton in our streaming storage. And the data will be moved from that streaming storage to the historical storage, primarily based on ClearHouse. You can see there's a path, and we want to minimize all the kind of unnecessary data marshal and marshal. For example, like if you save data in no matter Kafka or Repanda in one format, and you move the data copied to your ClearHouse, there will be data ClearHouse format. Then you end up with two formats, right? And if you want to do some buffer between the ingestion API and your streaming storage, you have the third format. So that's, if we're talking about single digit milliseconds, keep doing marshal or format transformation is something we try to avoid. So we come up with our own data format, which is a consistent for indifferent layer, no matter in the memory, in the streaming storage, or in the historical storage. So that format, we smartly call this as a Timeplus data format, or TDF. it's implemented in the open source Python side, so feel free to check if you have interest. But in short, it is format with maybe two major goals. One is to minimize or completely reduce the marshal in different components. So it's a single format in memory, in disk, no matter in storage, streaming storage or historical storage. And the other part that is we try to design this format in a way it can give you the best possible performance. For example, in this format, we have this 10 step. We have a very compact way to compress the data, and we can have other semantics for our future streaming processing to benefit. So it's very good format for you to do scanning, to do some kind of a sig. So this is not really available in either Kafka or in Clickhouse community. So in short, the one of the secret sauce that is we have this unified data format TDF, and the TDF leverage even some of the new idea from Linux, for example, the IOU ring. So there's some interesting stuff we can leverage in the latest open source or in the Linux kernel. And we put this into our design of the file formats. And this format is consistent in the memory, in the streaming storage, in the Clickhouse side. So Clickhouse, in our case, it is a good foundation for the OLAP, but we changed the data formats to be more consistent and efficient. And also we also realized there's some common challenge for Clickhouse users, right? For example, it is very fast for single table, big scan or aggregation. But if you have multiple tables, you want to do join, I guess it's a common, I would say, at least it's common impression that is Clickhouse is not very good joining multiple tables. So there's some theory that you should using this OBT one big table if you deploy Clickhouse. But it's not the case in Timeplus because we focus so much on the streaming side, and it's very difficult or very expensive to have everything in a single topic. You have to join with other data.
Yeah.
You have to join stuff like the mention table, like your employee ID with your name or the stuff, but also you can join with other changing data, right? No matter it's slow change data or fast changing data. For example, this is your transaction, this is your user login, this is your server workload. Everything is changed and you want to build a good understanding about the whole picture. So the join is not something you can avoid in our case.
Yeah.
So that's the reason why we focus a lot on the join enhancement based on the powerful Clickhouse code, but we really make the join much powerful and easy, and also resolve that small batch insert issues, as I mentioned earlier, and also works very well for our own code. And in the end, Proton can be very easy to get started as a single binary if you want to get hands dirty to process data. But if you want to deploy in the production way, for sure you need a cluster, right? Then in that case, you just deploy multiple process, no matter as a Kubernetes network, or even you using Docker Compose, or if you want to do as risky as the bare metal, you can do. But we also have our own clustering API so that those different nodes can talk to each other to know who is the leader, for example, who is the follower, who is the main writer, who is the reader, and how to fail over all those fun stuff. Or you can do even as simple as those Proton individual servers don't talk to each other at all. They leverage Kafka. For example, if you have 10 different Kafka topic, each one can consume one topic. Or even if you have a huge topic with a lot of different partitions, you can grab different partitions. So you can do this in the kind of a parallel way without set up a cluster of they can talk to and grab the different partitions. So there's many different options, really depends on the use cases.
Makes sense. A couple of things you mentioned, very interesting. So one is the data format. You mentioned you don't want to marshal and unmarshal between different systems. So one data format that works for all is great because you avoid the cost and effort of marshaling and unmarshaling whenever you do, let's say, analytics, or when you store data, or when you do streaming. So you have one data format for all of these three use cases, and they're all glued together inside one process. And I want to focus more on the production side of things, where I have a cluster and I have multiple Timeplus process. And so there's a cluster, data is coming in, let's say from Kafka or something. And then how's the data partitioned, and how does it choose a leader and different followers, and how does that part work?
Yeah. So again, this is really a database podcast, right? So I'm happy to talk about some topic. Again, so I think this is a lot of inherited powerful feature from Clickhouse, but also we, as a company focusing on the streaming side, also try to build a good open source project. We have some enhancements, even some breakthrough. Let's take a step by step. For example, if you have a single Proton server or deployment, in the simplest way, you have a single shard for your data, right? So in Proton, we call everything as a stream. So we just somehow rename the ClickHouse table to stream. So you can like show stream, but the show table also still works, but tell you there's a bunch of streams. So everything is a stream. And every stream, every row we call underscore TP time, which is, we are Timeplus, right? So every data have a time, no matter what, right? So even you upload a CSV file, we have a time regarding when this is uploaded. Or if you prefer choosing a certain column as your actual event time, you can do. The time is so important in Timeplus Proton. And for example, you can imagine our index, or in the term of ClickHouse, is key. It's primarily based on time, right? So you can naturally have your file structure optimized for time, so that you don't have to scan all the folders, all the files. You go to that particular folder. But again, in a simple way, that is by default, every stream have a single shard. But even in a single server, you can still have multiple shards if you choose. Right? Then, for example, you choose I want 3 shards for my single Proton process. Then there will be, for example, like 3 folders, right? Then if you do this carefully, if you mount your file system in a clever way, it can give you a better chance to improve the performance by leveraging the multiple concurrent IO disk, right? So this is the shard. Then very similar to other systems, we have the concept of the replications, right? Yeah, again, if you have multiple servers, you can set up different shards, different replication policies. So it is pretty much very, very similar to, for example, like from Kafka. Right? Kafka also have the idea of partitioning. I think partitioning and shard, they are almost the same term. And they have the idea of replication like this. For the same partition, how many replica you want. Then you also have idea about have the metadata server, who have the full picture about which partition is in which server, stuff like that. And we also have our, say, Raft implementation. So also that's can be an interesting topic. That is, for a while, people really enjoy, at least for the Java ecosystem, enjoy Zoomkeeper. And now people are talking about how to avoid Zkey. Even ClickHouse, they use the Zoomkeeper for a long time. And now they have this Clickkeeper, or just they call Keeper. And in Kafka, they also have this new Zoomkeeper free version or configuration. Yeah, because when you have a lot of data, a lot of servers, Zoomkeeper can give you a lot of features, but there are certain limits. It depends on how large your scale is. You might hit, or you might be okay, but you might be hit for that limit. In our case, we don't really want to make our deployment or component too complex. So we try to avoid Java if possible. So we don't really consider Zoomkeeper at the first place. And I think the ClickHouse or Clickkeeper is, A, is new. B, it is very optimized for ClickHouse own use cases. For example, they are talking about the parts or the different stuff, which is not always relevant to us. So we implement our own simplified Raft and for the lead reduction failover things. And as a kind of production usage, you set up a cluster of Proton, and they talk to each other to making sure who is the kind of leader and designing this failover process.
That makes sense. And it looks pretty, as you mentioned, pretty standard, like how other databases are doing, how data is partitioned and how it is stored and how the consensus is maintained. And so you pretty much try to use what is available in ClickHouse, but what works best for you, right? You try to modify that. So Going back to our example of ingestion, let's say there are stock prices coming in and we know how the ingestion is working. There's a cluster of Proton and it's just one binary in just one process that gives you analytics and streaming. So analytics part is clear where there is ClickHouse like data store, which you leverage, which you store the data and do that. Also use it for querying. How does the real-time streaming part work inside Proton and what kind of data store are you using, if any? How does that use case work? For example, so I have this stream of stock prices coming in and I want to write a SQL query and I want to understand, let's say that the top 5 stock orders given in, let's say, last 5 seconds or 5 minutes, for example, and compare it with, let's say, the trend of, let's say, last month, the same time, something like that.
Yeah.
So I want to have a little bit of historical context while comparing the real time transactional processing with, let's say, last month's data or even beyond that. So how the streaming part and the analytic part are unified together to give like one insight from this query.
Yeah, sure. Yeah, it's a very good example. And I recently recorded more like a video tutorial for this. Feel free to check. So in Timeplus, CQ is our primary interface, right? We do support stuff like Python or Java or JavaScript SDK, but CQ is the primary interface. And we believe that CQ is maybe not 100%, but cover a lot of cases. In many cases, you don't have to write your own code. So in your case, that is, you want to understanding about what's happening for the past 5 minutes, but also you can be as aggressive as past 5 seconds. But you can also want to compare what's the pattern in the past 3 months. It is very common, and figure out whether there's some signal or some action you should be doing. So in Timeplus, we unify this streaming and a batch, but we still need to be very clear what's the kind of the expected kind of a query behavior for the engine for a particular SQL. We cannot guess, right? We can talk about AI a bit later, but so how things work, that is, in Proton, when you run a query, say, select a star from XYZ, such a very simple query, we run this in the streaming mode by default. Again, there's some, when I say by default, there's some other tuning. If you change some config file, if you change some port, you might change this, but let's put it very simple. If you start a Proton Docker post or Docker image today, you run such query, it is running in the streaming mode. So all the data is coming to Proton, no matter using Kafka or you have the other terminal writing this into. Once you insert, that kind of data will be show up in your result. This is the streaming query. We start the query, never end until you cancel it, and it keep waiting for the result. No matter you want to do this simple, we call streaming tail, which is come up with an event and see the new event, or do some aggregation, right? And aggregation, you have to aggregate a certain data together, then you have to have a certain boundary, right? So for example, in your case, you want to, hey, what's my past 5 minutes or 5 seconds? So it's actually a moving window, right? So this is the boundary. Or if you want to count, say, the number of transactions in this Black Friday since, say, 2 weeks ago, but you can do this incrementally. You want to get the results every 1 second or every 2 seconds. This is we call global aggregation. So there's a few semantics regarding what do you expect the time window. We are talking about unbounded stream for sure, but come to the real stuff. You don't want to wait forever. Right? You want to get the real-time update, the real-time numbers. So you come up with certain, either a window or a certain interval for you to see the new results. So that's the streaming part. So by default, it is the default mode when you run a query in Proton. And if you want to query the data in the past, we just wrap out the stream name as a function called table. So you wrap this as a table function, then this selects a star from table in this as your stream name. It will go back to our streaming storage, which is largely based on ClickHouse code base, but not a ClickHouse server per se. It's just leverage the code, but it's still in our own code and component and the binary. Then in that case, it will read it from the streaming, read it from the historical storage. And Select star is a bad example because it will scan all the data, which is not really good. But if you do stuff like count star, then the interesting that is the data, you don't have to scan any piece of the row most likely that count number is available already in a small file in our storage. We just read that piece of data, like this is 1,000. We just read that particular 1,000 to us. But next time when you insert new data, that file will be updated. This is very common how index work, right? Or some other index like min-max index, or some other index work that is you keep computing the results you want, and you don't have to scan data or minimize the data. So you read the value of the index. So in that example, the Slack count star from the table XYZ just read our data in historical storage or most likely from index. Then you can do things together, right? So in SQL, you can have something like subquery. You can select from, and this is the other BigQuery. Or you can have fun things like we call a CTE, the common table expression. You can have a with A as a query and B as a query. You can A join B. You can do very interesting stuff together. And every single subquery can have their own semantics. Like, for example, this subquery can be streaming, this subquery can be batch, and you can using this from or using this select, or even you can using stuff like union or except to combine multiple data sets together. So in the end, you can have a single SQL, and no matter it's 1 line or 100 lines, give you accurate results based on which mode you are using for each CTE, and give you the results. In your particular case, that is, you can get the last 5 minutes or 5 seconds as a aggregation result, and you have the other CTE to using the table function to get the kind of a pattern in your past 3 months and see whether they match to each other and in a single query.
Okay. That makes sense. And so there is 2 parts to it where, you try to get the old data from your storage engine, which is similar to ClickHouse. And then the real-time streaming is happening. Is it all in memory, or is it also using, let's say, for example, Kafka Streams uses RocksDB for storing some of the results of the computation, for example, or some aggregation values? Or so how does that work? Are you again using ClickHouse for that, or it's all in memory?
It's mixed, right? So, for example, depends on you or your audience how familiar you are for Kafka, right? So it is, for example, Kafka is a great system, but it's not really accurate to say 100% is in memory, right? So they have a lot of stuff in the disk, in the file format, but also there's some stuff in the memory side. It is very similar how we do in our case. That is, some data is in memory, and we have like own version of Kafka, but not so general purpose as our streaming storage. We have a special name called as native log. The reason we call native log, if you are familiar with the concept of the Red Hat log, the WAL. So this is actually put the Red Hat log in the stream storage or in the Kafka in a native way, so that you have more like a message bus, but every single piece of the data is the Red Hat log. And you design your method format, which is the TDF, the Timeplus data format, carefully, then you can end up with a good way to store your data and have some powerful seek-to or some time travel capability. In short, that is, this is largely inspired by Kafka. That is, we do buffer or cache certain stuff in the memory, but we also leverage the file system, especially for the FSD, to have a very powerful and low latency streaming storage. We also look into some other configuration option for you to leverage object storage, for example, like S3 or mini IO. But that's definitely we're introducing some extra latency, right? For example, you have to send data to S3 or you want to read this back. This can be option if you don't really care so much regarding latency. For example, those people from Workstream, they have maybe S3 based Kafka imputation. That's certainly doable, but that's not our default configuration. So by default, the data is in the memory first, then it's in the SSD, then even in that side, it will be in the streaming storage first, then it will be moved to or copied to our historical storage in the next 1 or 2 seconds. I even have a CQ I can share later on. That is, you can have a query to see what my next event and what is the event in my current storage and what the gap the gap is usually 1 or 2 seconds or even less. So that's the interesting part.
Makes sense. Makes sense. So basically, yeah, as Kafka uses this changelog topics internally for maintaining the state and making it durable, whatever you're processing in your stream. So I think it's similar concept. So you have a write ahead log, and which is you use SSDs to make sure it's performant. It's not taking a lot of time basically. And then you also mentioned there is a SQL query which gives you the time difference between, or let's say the latency between the next event and the last event. So it's pretty cool. And then you also move data from your the streaming storage to your historical, or let's say the analytics storage, which is ClickHouse based. And why is that? To leverage ClickHouse more, or why is that happening? What is the use case there?
Yeah, when I say move, it may not be so accurate. It's more like copy, right?
Mm.
So again, in the streaming storage, or our code name is native log. The native log have a rotation policy, like how long we should keep data there. Is that going to be 1 day or 1 week? And also in the historical side, based on ClickHouse, but we changed. I'm not sure whether this feature is available in ClickHouse community, but we also have a rotation policy there. You can also set how long you should keep this data movement, or the copy from the streaming storage to the historical storage is happening all the time, and with a very low latency, like a couple seconds. The reason why we do this is that the streaming storage, you can just consider this as a Kafka or Rapanda, right? So it's very good for some certain use cases, for example, like a continuous write as a buffer. But in terms of this aggregation workload, building index, it is not the best way as a format, right? It's because you can do some kind of a jump to a certain point, but most cases you have just scan one by one. It's very expensive to keep reading all the data at the same time. It is not really a column storage, right?
Yeah.
So by nature, you get piece by piece. You cannot say, because I get a new piece of data, I needed to deconstruct all my previous columns and add this data to this column. That's just too much. Streaming storage by nature is row-based, which is very good for streaming, but not very good for aggregation. That's why we leverage ClickHouse as a code base to do those amazing, not just about those index, those are min max index, count index, but also for example, if you check ClickHouse, they have so many different ways, or those are tiny optimization for the codec, for the compression. For example, a number, say you have this number, you can store the number as a map, or you can get the delta for each number and only save the base number, and this number is bigger than the other one. You only save 2 or 1 as a delta. Even some crazy stuff like it's called double delta. So you can measure the change between them. So the goal is to save as little as possible in the raw data, so you can get a very efficient storage, and also don't spend too much time on the CPU side when you want to read this. So we really trust the strong and the mature community of ClickHouse doing so. But again, we have good reason to have these two components in the same time. We have the streaming storage, meaning for raw, for the streaming read, streaming injection, but also the historical one, leveraging the powerful and efficient storage engine from ClickHouse. And the other thing is we not just copy data from the streaming storage to the historical storage. We also have some interesting stuff to smartly check, when I run a query, should I query against the streaming storage or query against the historical storage? So in Timeplus, we have this notion of, we call seek-to, or time rewind, or a fancy term called time travel, right? So as I mentioned, that is, you run a query like select star from XYZ, by default, they will start the job and waiting for the future events. But sometimes you want to show a dashboard. You don't want to wait for all the data come to light up your dashboard. You want to see the dashboard with the data in the past, say 1 or 2 minutes, with the new data, and you can shift to the left or right, whatever. In order to get the data in the 1 minute ago, we have this time rewind syntax. You just using TP time greater than now minus maybe 2M, which is 2 minutes. Then we will travel back to 2 minutes ago, starting from there, and read the sum of the existing data and wait for the new data to come. So that part, naturally, it will be reading our streaming storage. But in our recent versions, we can detect whether, if you're asking about 2 minutes or let's say 2 months, whether that 2 months data is still available in the streaming storage. If no, then please read the data from your historical storage and move the data from the historical storage to the streaming storage and to the query, or skip the stream storage to read it directly from the historical one. So can be optimized in a way that is, when you run a query, we can figure out what is the best way. If we figure out that is, if we can leverage certain index, for example, this const star, certain index in the Excel storage, it will be even faster than streaming. It's not always the case. Streaming storage is faster than, it really depends, right? Depends on your query. So we can do some interesting stuff by unifying two together. So as a user, we're even going to make some kind of a documentation change to avoid mentioning too much regarding the native log, the streaming storage. So as a user, you only needed to care, hey, how long I should keep the data? Like, I want to keep for 1 month or keep it for 1 year. And you just only set one rotation. And that rotation actually will be in the historical side. Then we can give you a default value for, we default to give you 1 hour or 1 day. Then you don't really have to care that too much. That's become kind of our implementation detail as a buffer. Because in the end, you get all the data you want in a reasonable fast way.
That makes sense, and I like these small concepts where you don't know exactly which one would be faster, right? Because one, let's say, is row storage and one is column storage. The amount of data is different. Be in the historical, it can be in the streaming one, or it can be in the historical one. So there's a lot of analysis involved, and I guess it's happening all while the queries are served or the data is served. So just to close this loop here, how is the data served back to the user?
So that's multiple way. One is, if you run this in your terminal using our Proton client, it's just leverage the fundamental stuff from Clickhouse. For example, that supports say A12, and this is using the TCP protocol from Clickhouse, because Clickhouse community is very focusing on the performance. They have a lot of different HTTP, TCP, different ways. So we just inherit that features. So using the native prot from Clickhouse. And also we, as I mentioned, that is when I say default, there are different ways you can configure as a file, but also you can using different port. For example, this A123, which is the same port as Clickhouse, we enforce the batch mode. So in the example that they use, run select a const star from table. If you run this in the normal mode, it will be stream mode. But if you run it using this Clickhouse mode, it is actually will be automatically in the batch mode. You will query directly to the historical storage. Then we have different ports. That's one part. And the other thing that is, we also provide the REST API. And the REST API, also, if you check our demo systems, we have quite, I would say, very impressive UIs with the very live data, very live dashboard. And that is actually come through our integration with the UI using either WebSocket or server-side SAN SSE. The reason I use say or not is because we try both. Like we sometimes I prefer WebSocket, sometimes we prefer SSE, but they are all very good the knowledge. But as a user, it is very nice if you can have a real-time dashboard. Data is changing all the time. You don't have to refresh. But that is through either WebSocket or SSE. And so in short, that is for the serving layer, you can leverage our Clickhouse like ports or the TCP or HTTP protocol. We have different ports with different default behavior. We have UI integration with WebSocket and SSE. We even provide like JDBC, ODBC drivers, right? So that as a user, you don't really care too much. You just use as if this is a Clickhouse, for example. We are even get some requests to support what is called ADBC, the Arrow database connectivity based on Apache Arrow, which is coming.
Very interesting. So if I have to, based on our discussion, if I have to talk or pick, let's say, top 3 reasons why Timeplus is so fast and what enables you to deliver all these insights such a low latency manner, I would guess, and you can correct me and you can add more to it. So top 3 reasons would be, first, you use Clickhouse, which is one of the fastest available analytics data store. It is highly optimized for that. Two, you avoid the marshalling and unmarshalling as you use the same data format, which is a custom Timeplus data format, TDF. And third one, which is you avoid the latency of talking to the analytics store as well, because it's all in one process. It's not like Clickhouse is running in a separate cluster or something, right? So these would be my top three reasons why what makes Timeplus fast based on our discussion. But what are your top three reasons what makes Timeplus so fast? What are the top three reasons?
No, I think you captured very well. You are a great, a faster learner. I think I probably will give the same answer. Yeah, so even we talk a little bit about the language, right? Again, the reason why I choose Jove as my English name is Java lover at the very beginning, 20 years ago. When I tried to choose the name, I have to choose one, and the Java lover. So I don't hate Java for sure, and I do also respect stuff like Kafka or Flink, Spark. There's a lot of good stuff from Java world. Then in the case of data streaming, there are more and more cases people want a native engine, right? So even Databricks have this paper published, I don't know, maybe 4 or 5 years ago regarding their native implementation of Spark core engine. Available in their commercial or cloud, but it's not open source yet. There's also some open source attempt from Intel, from Engines. So it's still very popular in the big data area, but in the streaming area, Flink and Kafka, Spark, they really give you good foundation. Or if you prefer do some kind of enhancement or troubleshooting, Java may give you a little bit more confidence, right? So you can debug, you can check how code works. But if you're looking for super low latency as low as single-digit millisecond, as we can do for some of our fintech customers, Java is not always or it's not your only option, right? So that's more and more system written in C++, written in Rust, or in some other new languages to try to, is minimize the GC. No matter how good those new GC, I know there's tens of different GC, and there's even a lot of JVM provider, right? They come up with some commercial or even some paid version of JVM to do even better performance. But again, GC is something you can optimize, but not avoid. So there's still some GC, and when the GC comes, the entire world free. So that's not great if you're talking about. And also other stuff that is JVM don't really give you low-level access to, for example, IOU ring or some other Linux kernel features, or even some chips level stuff. Like, for example, column storage like Clickhouse, they have a lot of enhancement SIMD as IMD. So those stuff is not easily can be leveraged by Java world. Even, for example, RocksDB is popular in many of our Java projects, but it's a separate process, and you might hit a certain IO limit or CPU limit. With C++ as our own database language, well, we use other language, for example, Golang in our cloud side, but in database, it's just C++. So we also in a single code base, we really can push the limits. We can say sorry to some other customers. Sorry, we don't support this version of Ubuntu, this version of Red Hat, because we need to give you a better performance. Please upgrade to the latest Linux kernel. In many cases, it works, and they really see the difference. The language is not always the case, but it gives you certain different options. Then this is more like all-in-one or single binary philosophy also give you more room to improve. So actually in our early versions, we try to leverage, say, Rapanda, we try to leverage Clickhouse to actually concept-wise its work, right? But you either save data in different formats, or you transfer data from one side to the other side, or you talk to each other using, for example, TCP, which is okay, but may not be the most efficient way. And by building our own version of Kafka, of Flink, and also largely depends on Clickhouse, but we have had some enhancement, for example, the storage format. We get a much flexible way to enhance the way we can do. Yeah.
Perfect. It was an insightful discussion, and I never like to end the session because I always feel that we are just getting started. There are so many interesting things, but unfortunately, in the interest of time, we have to end this session here. I believe we have added good basic understanding of how Timeplus is working and what makes it so fast and why fast performance is required, right? And how does it compare with other solutions? I think it will be very insightful for anyone who is generally interested into understanding streaming systems and what are the options available and how things work internally. So thanks, Joe, for joining us today and sharing all the internal details of how Proton and Timeplus works. But yeah, unfortunately, it's all about time and we have limited of it. So yeah, we have to end this session here. But thanks a lot, Joe, and looking forward to release this episode and also getting feedback from our viewers.
Yeah, time is always matter. And what I said today, you can always check our code. And so check our Proton repository. And looking forward to see your feedback. Join our Slack, give some feedback, or check our cloud. So we really want to work with all the developers in this space to achieve a lower latency, to see what's happening right now and create amazing solutions together.
Thanks a lot.